And we will see if other folks join us. Okay, the first thing I want to do is I'm going to go ahead and share my screen and just again, kind of want to look at the homework. Yesterday, we ended, or not we ended, but we did look a little bit at the turning equations, and we looked also at the milling equations a little bit as well. So if I, of course it's not going to work. It worked when I was practicing. Let me see if I can get this to, if it doesn't want to work, then do it the old-fashioned way. That's interesting. There we go. Okay, so for condition 5, where we're looking at the half-inch tool, there's that 2 cutting surfaces, table speed 27 inches per minute. I'm going to just leave this up a little bit. So for some of these, notice that our width of our cut is 1 inch, but with a half-inch tool, we're going to make 3 passes. And so when we look at our material removal rate, we basically look at the width of our cut divided by the number of passes, and then our depth of cut and table feed, and we get a material removal rate of 0.1833 cubic inches per minute. Our feed, which again, our feed is going to be in inches per tooth, and small f feed is off feed, and then speed, we have it what we set the machine, but we also have the cutting parameters. So that's going to be our table feed, our spindle speed, and number of teeth per or cutting surfaces. So we get 0.006 inches per tooth. Our speed, again, the equation is pi dn. It's the same in milling versus turning. And so here we have our pi, our half-inch, our spindle speed, and then I just go ahead and convert some inches to minutes, and we have 301 feet per minute. And that also would be an SFM. Our power is 0.055 horsepower, and then our cutting life, tool life would be 3.34 minutes. So again, this is a partial example for one of the conditions in your homework. Okay, so we should be good to go on our homework. And if we look at where we were at the end of class yesterday, we had been discussing, again, the important results for machine parts. So one of the things that I think is important is to have an understanding of the relationship between the inputs and the outputs. And again, surface roughness is going to be related more to feed, so that's going to be F, and tool radius. Our tool life is going to be related to speed, so that's that feet per minute, the tool material and workpiece material. And then on the dimensional tolerance, we want to look a little bit at our fixturing, to some extent, the tool selection, and then sequence of steps. We know that we want to minimize bending. So if we have any bending, we're going to have less accuracy. We also want to try to limit the elastic deformation, because that's going to also make our dimensional tolerances not as good. So basically, we cannot get as accurate. Okay, so here's one where, again, if we're looking at clamping and holding, if we have this situation where we have more of our cantilever beam, we're going to see deflection as we machine this top surface, whereas if we have the material supported, we're going to get less deflection. And so when we consider sort of not just the sequence of operations, but also sometimes the design of the part, sometimes we do need to get some creative fixturing to make sure that we're always supported. That is something that we can look at. We also, in our reading assignment, looked at the advantage of having multiple axes and not having to reclamp the part as much. And then we also have this particular situation on whether or not we would want to sort of do the groove before the hole. If we look here, and one might say, well, kind of look at material removal and tool life, that's often competing with dimensional tolerances. But if we drill this slot, if we machine the slot first and then drill the hole on the right would be fine, but on the left, we're going to get significant deflection on this top piece. However, if we drilled the holes and then cut the slot, our overall dimensional tolerance would be better. So again, we just need to kind of think about these are factors that are not inherent in the process itself. This is how we would do the process. And then one of the last aspects that I want to talk about is just to kind of consider the costs that go into machining. The line up here is our total cost per piece, and we're doing that versus cutting speed. So again, that is going to be the cutting speed is V, and we know the parameters that go into that: tool diameter and spindle speed. What we see is that as the speed increases, our machining cost, which is basically related to time, so this is going to be time, goes down as our speed increases. Well, that makes sense, because if we'd have a higher material removal rate. However, if we look at our tool cost per piece, that goes up as our speed increases, because speed is related to tool life. There's also a cost for the tool that we might not think about, and that is the downtime for the tool changing. So our total tool time, our tool cost, and the time associated with the tool changing, this goes up as the speed goes up. So there is an optimal speed that minimizes the cost per piece. If we are at a lower speed, then tool life is higher, but our machining time is also, tool life is higher, but our time is also higher. If we go a little bit if we go on the other side of that minimum, then our tool life starts to go down and the tool costs go up. So again, just we want to kind of always have in mind some of the costs. And then we will talk about a couple scenarios going forward. And so a lot of times what we may do, and I believe that it might have been mentioned in one of the videos, is that we tend to have, and in our textbook, we tend to have roughing cuts. So where we want to have a very high material removal rate, we want to just remove the material, get the basic shape, but where dimensional accuracy is not really a factor. And then we have finishing cuts, and here we actually are not looking to remove a lot of material. So we really wouldn't even look at efficiency of our material removal. Because what we want to do with these finishing cuts is get the surface finish and dimensional accuracy. And oftentimes, we may actually use a different tool. And that is, of course, I have that different tool on the next slide deck. I didn't have it here because I often might bring it to class. And of course, I had it yesterday, but not today. So a lot of times, if we kind of consider for our finishing cut, the tool is different. The geometry is going to be different. The amount of material we move will be different as well. Okay, so I think I'm going to pull up. Okay, I'm going to just pull up my, I'm going to pull up a slide from the next slide deck, but here we can look at our drill bit. This is often sort of more of a rough cut. We establish the hole, and then the reamer. So both of these are actually a 1/2-inch tool. So and it looks like the drill bit often just looks larger, but they both are for a 1/2-inch tool. And then the reamer, what the reamer is, the intention is to sort of improve the dimensional aspects of the hole. And if we think about what are some dimensional aspects of the hole, it's like how close to a perfect cylinder is the hole. Notice that the reamer, the geometry of the tool is very different. We have we don't have these sort of more aggressive flutes. The cutting surfaces are just in one direction. And again, this is really just intended to remove small amounts of material to kind of make the hole more of a perfect cylinder. Okay, so that really sort of finishes up our standard machining. We do again have our homework to do. If we consider or look at labs, what we're going to be looking at with labs are next week, you have time to work on your casting project. Week 8, we're going to be looking at doing some surface roughness analysis of some machine parts and also look at some machined parts, plastic parts, and powder metallurgy parts. So that's kind of what we're looking at. Okay, so depending on how things go, we might look at a couple video clips today, but let's move on to additional material removal processes. And so sometimes these are considered alternative processes. These are no longer generally considered chip formation. We can put these processes, we're going to look at these in 2 different categories. And the first is abrasive processes. And we're primarily going to be looking at the abrasive processes for finishing, specifically honing and lapping. And then we're going to look at 4 non-mechanical material removal processes. And those are flame cutting, electro discharge machining or EDM, laser cutting, and then water jet machining. And so all of these have different advantages and disadvantages, and we want to kind of look at the overall process. So you may or may not remember, probably not. I probably wouldn't remember if I didn't look at the particular graph a couple times a year for a few years in a row. But abrasive processes were considered chip formation. But it's not really your standard chip formation. But if we kind of consider the action of an abrasive process, we have small, hard particles. The particles are likely to be, you know, they could be sand. That would be somewhat unusual. These could be, you know, a ceramic. So for instance, like a carbide or an oxide. Also, these could be our diamond or our cubic boron nitride. Generally, we're not going to see like a metal. So we don't usually, when we talk about these tools, these are going to be more of our ceramic type materials. You know, a lot of times we may, again, look at carbide on there. These particles will vary in size. And oftentimes we refer to the size. This is kind of where we can talk about like the grit size. If we're looking at this from a finishing operation, we're going to have very fine. If we're looking at these abrasive processes as more of a roughing situation, then we would have a much larger grit. Now, the particles generally have sharp edges and irregular shapes. So we're going to kind of look at this for how this is slightly different than our standard chips. So if we consider it, again, the cutting edge of the particles are randomly distributed. So we no longer have a controlled angle. Instead of a depth of cut, we talk about a depth of engagement. That's going to be small and not equal. And then we have generally very high speed, which means it's going to get hot because we recognize that the speed is associated with temperature. So while it is a sort of a chip-ish formation process, we cannot model it. We don't have the equation that we do for the other processes. Now, we do see with any abrasive process, the temperature increase can be an issue. And this is, again, mainly from the high speed. Because we do see this correlation between speed and temperature. If we have a rough process, we're oftentimes sort of looking at a grinding. This is going to be useful for like our hard, brittle materials. And we often do really just refer to this as grinding. This is how you might shape a, you know, your hardened steel, where you may be doing it to try and correct from some heat treating. But again, we're going to mainly kind of focus on the finishing. So from our finishing, here is where we can get excellent tolerances and smooth surfaces. So these are going to be able to, some of our abrasive processes can get surfaces and dimensional tolerances that are better than our standard chip formation processes. And that's why they're really referred to as finishing. And again, honing and lapping are two examples we're going to use. So we're going to look at. There are others, but if we kind of think about our chart, the smoothest surfaces were from some of these abrasive processes. Okay, so let's start with honing. And with honing, this is a process where we can give holes a very fine surface finish. So now, again, we can get down to 4 micro inches. Now, yesterday, we calculated a surface roughness on that turning operation, and I believe it came down to 128 micro inches. So that's a much rougher surface than the 4. Honing is intended to be done after reaming. So we would drill the holes, get the shape, ream it to make the shape, the dimensions of the shape better. It will help the surface. And then honing goes in and helps smooth it even more. Now, the abrasive is going to be bonded onto like a metal stick. And sometimes it's also called a stone. And so these oftentimes look like, and I have a picture I have a picture in the next slide that we can kind of look at. Actually, let's look at it now. So this is your stick or your stone over here. So there's like a metal carrier, and then the abrasive is going to be mixed with an adhesive and just bonded to the metal stick. Now, we get a very specific cross-hatched surface. So, and again, we might call this a lay. So honing gives us a very specific surface, and that's because we have these stones rotating and moving up and down, but we do get that cross-hatched appearance. So here is what the device would look like. We, again, see our honing stone, our workpiece, and as we move up and down, we start to get this cross-hatched pattern. So how might we use like a honing situation? I don't know how well this is going to really kind of come across. Here's an example of a honed surface. These happen to be measured in R sub Q, which is that root mean square as opposed to R sub A. But you can kind of see the path on the larger, and over here, this one's harder to see, but it does look like you do have that surface, and also it's much smoother. Here's examples of some different stones, and you can sort of see that the abrasive is getting, it's fine to start with, but it's getting finer. So a finer abrasive is going to give us a smoother surface. Okay. So again, I mentioned the sequence of operations. So usually you're doing this finishing operation after a couple other steps because you need that smooth surface. Honing is going to be done on a hole. And again, we start with drilling the hole to create the location. That's oftentimes we might call that more of a roughing cut. We then remove more of the material. So we would use a reaming operation. So we would have a drill or drilling operation. We then would have like reaming. So we use a reamer, we use a drill bit, and then our final process would be honing, and we may do multiple steps here in order to get a finer and finer surface. So how might we use this, or where might we want to go with a honing? A long time ago, I worked for a company that made corrosion-resistant pipes, pumps, and valves. And one of the things that, one of the things that existed is the material that had very, very good corrosion resistance was a high silicon cast iron. It was also a little bit on the brittle side. And for a pump shaft, you really want some toughness. So what our operation was, is we had a cylindrical sleeve that was made out of the corrosion resistant yet slightly brittle material. And we would attach that to a shaft that was made out of a carbon steel, you know, maybe a little bit of alloy content in there that had greater toughness. And so we attached the sleeve to the shaft in a process known as brazing, which we will talk about in a moment. But we needed really good surfaces in order to get good bonding. So we would hone the inside of our sleeves. So they would be cast, and then they were cast. We didn't have to drill because they were cast as a sleeve. We might do a little reaming, although sometimes we didn't need to do that, and we would go to honing and really get that very smooth surface. And that, again, that smooth surface gave us better bonding. You also may, I've also seen honing used in situations where I've seen small pumps, again, in the food industry, where you needed to make sure that you didn't have any pockets for bacterial growth. Okay, we've looked at the reamer and the drill bit. Again, sometimes these, they don't always come out as well, but this is that same sort of type of part we saw earlier. This is the drilled end, and then over here you can see the reamed end. You also will notice that there is not a crosshatch pattern. The surface roughness of these is somewhat different, but the reamed end also would be much more of a cylinder if we were to look at the dimensions. Okay, and then we also you take that reamed end, and we look at a slightly rougher honed surface, and again the crosshatched, and then the very, you know, this is almost getting as smooth as we can make it on there. So again, honing can get us quite smooth of surface. Okay, our other abrasive process that can help our surface roughness is something called lapping. Now, lapping can give us slightly better surface, so we can get down to 2 microinches. We can also, again, look at very smooth surfaces and accuracy. Now, here, the abrasive is a loose powder. Now, sometimes we might put it in a suspension, so sometimes we might kind of have it in a liquid. Sometimes it is just as the powder itself. We call the abrasive ends up being between the tool, which we call the lap. The lap can be flexible or it can be rigid, and the lap helps move the abrasive relative to the workpiece. So the abrasive is between the tool and the workpiece, and what we're doing is, if we want to kind of look at the surface, so here we have our surface that we get from like some sort of other material removal process. We've got the tool or the lap and the abrasive. And what we're doing is we're sort of just like removing the peaks. So after lapping, it's as if we removed some of those peaks, and that has really reduced the surface roughness. So here we would have kind of just an example. We oftentimes are going to be lapping on flat surfaces. We can do some curved surfaces depending on what the tool is. But the movement is, the tool is basically just going to be moving the abrasives to take off those peaks on the surface. Here is a die cast part, and then it has been lapped. So now these parts were coated with like a clear coat. So we have to take into account we're not looking at the direct surface because of the clear coat, but we can see that it is a much smoother finish from the original die cast part. So this particular surface was lapped, and then I believe it's coated after that. Okay, so here we're looking at, again, these are the two abrasive processes that are finishing processes that we've looked at. There are a few more. There's something like super polishing and a couple others. But in general, if we go with a smooth, small grit abrasive, we can get smoother surfaces. Okay. Now we're going to enter our next phase or additional processes. And here we might, we're going to kind of bounce around between the slides, and I'm going to see if I can attempt movies again, because I think that sometimes that's very valuable. But on the other end is flame cutting. So lapping and honing can give us very smooth surfaces. Flame cutting does not. And we're really not going to talk a lot about flame cutting, but I think it's a process you should be aware of. So generally, we're talking about an oxy-fuel. A lot of times oxyacetylene is a common thermal process. So what we're looking at is basically melting and vaporizing some of the material. So we have oxy-fuel, meaning oxygen and something else. Acetylene is the most common. So basically, we just have an oxyacetylene torch that you light. The thickness of the flame or the torch is going to be the thickness of the cup. It can be by hand, or we can have it computer controlled. It is very useful for cutting thick steel, so it's useful for cutting steel, especially thick steel. And what's interesting is the steel provides additional fuel. So the energy that once you get this process going, the energy that the torch is providing is supplemented by the steel combusting as well. As you can imagine, we have your surface roughness is large, very large, because you actually are cutting with a torch. So we're not getting really smooth surfaces, and your tolerances are large as well. Okay, but it is it's certainly on the roughing side. and it's really good for thick steels. Okay. I'm going to go ahead and see if I can get this to work. So I am going to find, where'd my cursor go? There we go. So I'm going to unshare because I will need to get the computer. I'll just take this back a little bit. This particular video has quite a few. There we go. Okay. So there's quite a few processes on this particular video. Oh, that's not what of course I forget what I need to do. It's so funny watching old people try to attempt all this technology. Okay, so now where'd my little thing go? There we go. Let's see.
While cutting is being carried out on one table, the other table is being loaded or unloaded. The carriage that carries the plasma arc cutting torch also has an oxyacetylene cutting torch. The acetylene heats up the steel plate, and the oxygen, using the steel as a fuel, cuts the plate. For plates of greater than 30 millimeters thickness, the feed rate for plasma arc and oxyacetylene cutting is similar, but there is a cost advantage in favor of oxyacetylene. As plate thickness increases, then so does this advantage. However, this process requires a higher operator's skill to achieve a first-class result. CNC, plasma and oxyacetylene cutting is used where complex shapes are required to be cut, or shapes that have to be nested in a plate. Line following oxyacetylene cutting has the advantage that it is relatively cheap and simple to use, but less accurate. For the most simple jobs, hand cutting may be the best process.
Okay, let's see. I'll just go ahead and stop this for now. So again, I just think that like if you kind of heard a few things, good for steel, you could sort of see the process. In general, the thicker the tool or the abrasive or the flame, the larger the tolerances are going to have to be. So we can, oops, that's not what I wanted to do. Yeah, here we go. So I'm going to go in a little bit different order than my slides, because if we want to kind of see another one of the videos, we'll just sort of move it along. So that's flame cutting. It is, again, really good for very roughing cuts. The video was comparing it against plasma arc cutting. That's not really one of the processes that we're going to be talking about, but it is another thermal process going on. I think the next process that I want to talk about is water jet. And now water jet, so for every process, how are we removing the material? What is happening? So in water jet, we have a high pressure, high velocity stream of water. And the water is essentially, we're really like removing the material through really abrasive, or I'll say abrasive action. And it seems weird to think, well, like how much destructive force can water be? but it actually can be, you know, significant. And we are talking about very, very high pressure and high velocity. So we're just cutting a narrow groove in the material. And the groove we can cut is very, very thin. Now, we might add abrasive processes. I'm sorry, we may add some abrasive particles, which will help the cutting. Now, the thing is that for water jet, there's no thermal energy. Most of our other processes, oxyacetylene, electrodischarge, and laser, we are somehow vaporizing the material, which means things are going to get hot and we're going to influence the surface, and we have difficulty, or we could have difficulty, you know, cutting certain materials. Water jet can pretty much cut many different materials. And with water jet, if we have two materials that have different thermal properties, we can easily cut those as well. So that's where some of the composites come in. If you have, for instance, like a plastic and a glass, water jet can do very well with that. We can cut metals. Metals are a little more difficult, but we certainly can cut those. We may need to add abrasives. Plastics go very well. Paper, foam, fabric, again, composites, and food. Food is one that's kind of interesting because we may not often think about food products needing to be cut, and there certainly are other ways that we can do it. A lot of times for certain products, you may just have like a thin wire. But one of the, I was talking with an expert in water jet machining, and I was fascinated with this. You may go to the grocery store and you may notice, especially if you're looking at buying fish, it's quite common in fish where the packages are all, let's say, 4 ounces or 6 ounces, but the shapes are all different. And it's like, well, how is that done? Well, if a large fish when a large fish is brought in for processing, it can be scanned, and then you can do, like, there can be a computer that actually can separate that shape into, let's say, 4-ounce pieces or 6-ounce pieces. Then you can generate a CNC cutting, send that to the water jet, and then that's how you can get some of your pieces. Now, couple things. No heat is produced. So we don't have issues with surface integrity, and there's no crushing at the cut. That is specifically useful in comparison to shearing. So if you think about taking a cardboard box, which is, you know, where you've got, it's sort of puffy, and if you think about shearing a cardboard box, well, and so kind of think about taking your scissors or shears, you're going to see some crushing at the cut. Water jet, you're not going to see that. Okay, it's kind of fascinating. We actually used water jet. I've used water jet in the diamond making business. And so again, over here we have like a water jet machine. These aren't necessarily very complicated, but if we sort of look at what we have our fluid. You're going to have some sort of accumulator and controls. And then you oftentimes are going to have your nozzle, which is going to control the stream, is oftentimes going to be sapphire or another type of jewel. We have our jet, and it basically goes into the workpiece. And again, you can see in the video, that's the next one that we can see. Some examples of parts that were made by water jet. This puzzle, I just think is fascinating. Of course, it's a company that can produce water jet system makes it, but this was all cut by water jet. So you can sort of see the level of detail you get and how small the cut is. These parts were all, again, cut by water jet, as well as this is a little bit of a thicker material. One of the things that we do that we are going to be interested in is how fast is the process, and we might want to look at, and as we watch the video, we can kind of, again, see this process. So I'm going to see if I can attempt to do this again, and we'll just watch the water jet aspect, and then we'll call it a day and start on this again on Monday.
Water jet cutting is ideally suited for cutting materials that are fragile, difficult to cut, or are affected by heat. The feed water for the water jet is filtered to remove particles down to 1 micron in size, as these may damage the pump. The accumulator smooths out fluctuations in water pressure and also acts as a safety device. The working pressure for the water jet is 345 megapascals. Water only is used in the water jet for cutting plastics, wood, rubber, carpet and matting. But for harder materials, ceramics and metals, an abrasive is added to the water before it enters the nozzle. This 10mm glass plate is being cut at a feed rate of 150 millimeters per minute, and the width of the cut is 1.2 millimeters. Water jet cutting is ideal in situations where heat or high stress would damage the workpiece. How else could you make this shape? When a batch number of some hundreds of this very large aluminium alloy spanner is required, the shape is developed and nested on the CAD station. This data is then transferred to the machine's CNC controller. This 16mm aluminium plate is being cut at a feed rate of 150 millimeters per minute. The first and every following 20th spanner in each run is checked for dimensional accuracy. The tolerance on the spanner is plus or minus 0.2 of a millimeter, and the edges must be square.
Okay, so again, we will come back to this on Monday and kind of do a little bit of comparison on these processes. We are going to be interested